tell us more about markets and equilibrium computation. So thanks for coming, Martin. Thank you others for coming, and the floor is yours.
Thank you very much, Sven, also for all the organization and to all the organizers. Very happy to be here. I'd also like to thank the speakers that we've seen this week. So Rakesh, Moshe, and Garrett. I had a wonderful week and enjoyed their presentation quite a bit. I'm going to draw quite a bit on what Rakesh has been telling you. So in this series of lectures, these two classes will be on markets and equilibrium computation. So the first part will focus on competitive equilibrium on large markets where the participants are assumed to be price takers. So this is very much in line with what Rakesh has already told you. And the second part of the talk, here we focus on somewhat smaller markets where bidders or participants on these markets are powerful enough to influence the prices on these markets. And here we draw on a different equilibrium solution concept, namely Bayes-Nash equilibrium. Both topics are heavily ingrained in optimization, as you will see. So the first is rather in the scope of mixed integer programming. The second is more in the realm of convex optimization. Right? Let me mention that I'm very grateful to my collaborators. So at the bottom, you see a number of PhD students, and the material that I'm going to present draws on much of the work that I've been doing with them. Eleni Bazio, Max Fichtel, Richard Littmann, Stefan Waldherr, Stefan Heidekröger, Nils Koring, and Matthias Oberlechner. Yeah, this is, I'm drawing in many ways on this joint work here. So let me start out with one of the most fundamental results in economic theory, which are the welfare theorems. And these welfare theorems go back to Arrow and Debreu and also Mackenzie in 54. And roughly what they tell us is that a market will tend towards competitive equilibrium that is weakly Pareto optimal. And the second welfare theorem essentially tells us that every Pareto efficient allocation can be supported as an equilibrium by some set of prices. So what you see on the left is this bird's eye view on a market. This is a partial equilibrium model, not a general equilibrium model. So we only have one type of good. And this kind of explains these Marshallian demand and supply curves, how prices are being determined from a bird's eye view. And the Arrow-Debreu theorem essentially tells us that an equilibrium exists also in multi-commodity markets. Right? So this is an affirmative statement that markets can solve distributed resource allocation problems. It hinges on a number of assumptions, though. So the first is goods are divisible and preferences need to be convex. Also, the bidders are assumed to be price takers, right? So they don't act strategically, and we will relax this assumption in part 2 of this class. And it's a pure existence theorem. So it draws on Kakutani's fixed point theorem. So it doesn't necessarily tell us how to get to these prices, right? So what I want to do in this class now is I want to discuss with you when do markets with indivisible goods have a competitive equilibrium. And here I have the luxury to draw on a lot of material that Rakesh has already told you. And then I want to focus a bit more on how do we compute these competitive equilibria. And that is very relevant in many markets. Think about day-ahead electricity markets, for example, where we have non-convex markets and we need to find equilibrium prices, ideally, or prices that clear the market. So I'm drawing here on Rakesh's roadmap. This is really a slide that I borrowed from his initial presentation, as you can see. And what he suggests is, well, what we are ultimately trying to do here is we try to solve a welfare maximization problem. So why not formulate this as an optimization problem, right? And if duality holds, dual variables can be interpreted as prices. That's what he's already illustrated in like the single object market. And we will also draw on primals and duals quite a bit in this first part of the lecture. But there are also limits to this general recipe. By and large, we assume quasi-linear preferences. Again, what are quasi-linear preferences? So our participants essentially try to maximize the difference between their value and the price. And by and large, we assume in this literature now that bidders are not strategic, as I told you earlier. Rakesh was telling you quite a bit about when we can expect dominant strategies on these markets, when the VCG mechanism would work. And he also showed you that the assumptions are quite restrictive. So, but I will get to that a little later. But for now, assume we have complete information. We just want to find competitive equilibria. But even that requires some assumptions, and the unlimited availability of medium of exchange, so money, that will be one of the issues that we will discuss a little later. So what I want to start with is the assignment market. And that is a market that goes back 50 years now, so by Shapley and Shubik. And Rakesh has mentioned it briefly. I want to go a little bit deeper here and give you an example, because I think it's one of the really nice markets beyond the single object market that Rakesh has been telling you about. So it's a multi-item market, and yet you can satisfy a lot of important axioms, right? So first of all, let me explain maybe the picture on the right. What is specific about this market? It's really your weighted bipartite matching problem, right? So we have these bidders, calligraphic I here, and we have items, calligraphic K. And these bidders might be interested in multiple objects, but they want to win at most one, right? And these bidders, they want to maximize payoff as well, right? As defined before. So with these assumptions, we can get to a number of nice properties. First, the computation is simple. So simple means we can solve it in polytime. So you're all familiar with that. There's, for example, a Hungarian algorithm that solves this weighted bipartite matching problem, or assignment problem, how it's called in different literatures. But this property also implies a number of other design desiderata that are very desirable. One of those would be that we can compute Walrasian prices. So what is a Walrasian price, or Walrasian equilibrium price? We have for each of these objects in here, we have one price, and this is the same price for everyone. So you will now say, well, this is what we experience every day if you look at the stock exchange or any other market. So what is so specific about it? I might want to remind you that Rakesh has told you there are environments where we don't get away with linear and anonymous prices of that sort. Right? So we will get back to that. But in this market, with these unit demand bidders, we actually get a Walrasian equilibrium. It can also be shown that the outcome of the Bichler growth mechanism is in the core. And that implies group strategy proofness. Right? So not only do we have competitive equilibrium, also there are mechanisms, BCG would be one, but also a simple ascending auction that have simple dominant strategies for the bidders. So to be more precisely, an exposed Nash equilibrium. And with all this, and with this specific algorithm that I'm going to tell you about, we can compute the efficient allocation, or the one that maximizes wealth. Right? So this is your market designer's wish list, if you want. Right? And we will see that it's very hard to satisfy all of these designers throughout the axioms in other environments that are more relaxed. And most of the results here really follow from simple LP duality, which is also nice. So this is just the write-up of the integer program of this assignment problem. So this should not be much of a surprise in what you see here. We have these valuations, VIK. So again, the calligraphic I is the set of bidders, and K of items, and XIK is the decision variable. And we write this down here. It's a binary variable, but we can relax it here. And due to total unimodularity, we would also always get an integer feasible vertex. So what you see down here should also not come as a surprise, is the dual of this primal problem. And the dual variables can be also found here. And the first set of duals of the constraints on the items, so each item can only be sold once, and the dual can essentially be interpreted as the price, the linear price, or the opportunity cost. And pi here can be interpreted as payoff. And if you look at this dual constraint here, right? If you rearrange terms, then you would see pi is more than VIK minus P, so the value minus the price. And this is what we are after, right? So we want to maximize payoff. So if you were to write down the dual complementary slackness condition, then you would get something like XIK times pi I minus VIK minus PK. Needs to be null, right? And so if XIK is 1, so if I assign a particular item to a particular bidder, then this means this constraint is tight. And if this constraint is tight, it means my payoff, pi I, is nothing else but the value minus the price. Right? I was telling you that there is a simple ascending algorithm, which is essentially the Hungarian algorithm that models this market. And Sven has actually published quite extensively on related models here. And I want to show you a very simple example just to make the case, because I think it's so nice. And it's really a straightforward extension of the simple clock auction. Right? So let me start with this particular matrix here. The asterisk marks the optimal allocation. And in each step, each of the bidders, I here, they would reveal their demand set. So you give them a set of prices. Originally, the set of prices is the null vector. And at this vector, all the bidders would pick the boxed entries here, right? So they would reveal to the center, to the auctioneer, that B is their preferred demand set. Right? With this, we have over demand on B, and we would increase the price to 1 here. So this would be our new price vector. And now we can just deduct this price here from the value. We would get a new matrix, if you would like. Again, we have over demand on B, and we have a new price vector, 0 to 0. And we do the same trick again. Now we have a minimally over demanded set of items, A and B. So this means if I would remove one of those items, it would the rest would not be over demanded anymore. So we can now increase the price on A and B. And we do this again, then for the next iteration, then this is the new price vector. And last but not least, we get this price vector of 350. And now we see that if you look at the demand sets that are being reported, so it's 2, 2, 2 so the first bidder reports A, B, and C in his demand set, the second bidder A, and the third bidder 3. So now we can find the perfect match, right? So we can assign C to bidder 1, A to bidder 2, and B to bidder 3. Right? So this is quite nice, and it's actually optimal allocation. And the nice thing is this is really nothing else but a more general recipe, a primal dual algorithm. Right? So this is taken from a book by Dimitrio that is probably very well known in this audience. And so we start out with the primal. This is what I've shown you earlier. We derive the dual. And then when we look at the dual, we look at those constraints that are tight in the dual, right? And essentially remember the very first iteration of the algorithm, where all the bidders were looking only at B. B was in their demand set and no other item. So essentially, you now set up the restricted primal. So the restricted primal can be really understood as a subgraph, right? This is 1, 2, and 3. This is A, B, and C, where we only consider those edges that are in the demand sets, right? And we just check then with the restricted primal and then whether there is a perfect matching. So every bidder gets one item assigned. So this is not the case. So 2 of the bidders will be unsatisfied. So then with the restricted dual, we actually determine which item price has to be increased. This would be B in this case. And we go back, adapt our dual, and go through these steps again, very much like what you've seen in the ascending auction. And indeed, at the end, we find an optimal solution and a vector of prices. Right? So this was very easy. And really, this algorithm, and that's maybe the new insight here, is we have an algorithm that serves as an economic model. So many models in economic theory describe sealed bid markets. So I think what computer science and math have contributed is really a more algorithmic view on markets and how to interpret algorithms as markets and market mechanisms. And then we can also describe certain properties. So this was all nice, but the assignment problem can be seen as a convex optimization problem. And when you look at this literature on competitive equilibrium theory, it really tries to understand, or a large part of this literature tries to understand, where can we get these valuation equilibria. So remember again, valuation equilibrium prices, linear and anonymous prices. And it's not restricted to unit demand. So there is a broader set of preferences. Strong substitutes, for example, is one of the sets of preferences that allows for these linear and anonymous valuation prices. But if you have strong substitutes, incentive compatibility is not guaranteed anymore, which we still had for the unit demand model, right? So, but you really try to carve out nicely when can we still get these nice linear prices, and that has a lot to do. That has been shown by a paper by Daniel and Mammer with the integrality of the allocation problem, right? So whenever this is integral, you can also expect these valuation prices and valuation equilibrium. So you're all in optimization, and it will not come as a surprise that many of the real-world problems that we deal with are not convex, right? So in leading examples are electricity markets. I mentioned them earlier. Today I had electricity markets are large non-convex markets. So for example, you have ramp-up costs when you power up some gas turbine or whatnot. So you need to model these as some type of binary variable, a discrete variable. So the LP relaxation, the straightforward LP relaxation, is not necessarily it does not necessarily give you integral results. Transportation tenders. So carriers in a transportation network, they are typically interested in round routes, right? So they want to start at some point and then want to get back to where they started, maybe. And if they have a trip where each lane is a full truckload, well, then they can give you a better price than if half of the lanes are empty. Right? Or spectrum auctions. We've heard a little bit from Moshe about spectrum auctions. So here, this has been an ongoing discussion, for example, in the States, that bidders, they have preferences for adjacent regions. So you get licenses, and again, Sven has been working on this also intensively. So bidders in these large regional awards, as they happen in the States or in Canada or in Australia, they want to get licenses in a number of regions, maybe some of them all over the US. But if they get a subset, they have cost complementarity, so synergies, if they get licenses in regions that are adjacent to each other, right? So this obviously has advantages for the end customer, it has advantages when you build up the network, and so on and so forth, right? So all of these constraints that I was talking about lead to non-convexities in the allocation problem. Right? It might be volume discounts, it might be package bids, such as what I just described in the spectrum auction. So you want to submit a bid on this subset of regions, and you don't want it to be divided by the auctioneer, right? So you say, I'm willing to pay an amount X for coverage of the states if I get nationwide coverage, but if I only get a subset, you know, I'm not willing to take that for the price, right? So the good news is that in particular integer programming has seen a lot of progress in the last 20, 30 years. So this bullet point here draws on a talk by Bob Bixby, who is behind Gorobi and behind Cplex, and might be known to many of you. So one of the leading solvers that we are currently using. And he was reporting empirical evidence and claiming that there was a 1 million time performance increase in solving integer programming problems in the last 30 years. And let me emphasize only on the software side. This does not take into account speedups on the hardware side. Right? So whether this is 1 million times or 500,000 times, it doesn't matter. So I think everybody who's working on integer programming solvers knows, well, we've really seen a lot of progress. Right? But in markets that are non-convex already, the allocation problem is non-convex valuation prices are impossible, right? So, and this is something we will see in a bit more detail later. And that raises the question, so how do we price these markets? I was telling you about transportation tenders, electricity markets, spectrum auctions. How do we get to prices in markets where we have non-convexities of that sort? Right? And the second question that I will go after towards the end is, well, often, and the leading example here would be spectrum auctions, and I happen to have been involved in several of those, you almost always have budget constraints. So suppose, and that would violate then your quasi-linearity, which was one of the assumptions that I was talking about at the beginning. So what happens if we have budget constraints? How does that impact the pricing problem? And we will see it's getting much, much harder. Okay? So this is now the agenda for the rest of this class. I first want to give you a real world problem. I was already talking about a few, but I want to convey this message here. Well, this is not pure theory without any application. Right? So there's plenty of applications, and whatever you've learned from Rakesh, it has many, many applications in the real world. Right? And the example that I want to talk about is trading fishery access rights, a project that I was involved with a few years ago. And also here, so this was a combinatorial exchange that we had to design and finally got to implement. The question was, we have package bits, so we have super additive valuations. So the fundamental allocation problem was non-convex. So how would we get to prices? So, and I want to discuss some of the different alternatives that are out there. And then also in this market, we knew that budget constraints would play a role. We kind of had to ignore them in a way. But from a pure theory point of view, we was then starting to ask the question, well, what happens if we do actually have these budget constraints and we do need to take them seriously, right? So how would that impact the resulting optimization patterns? Okay, let me pause here for a minute. Are there any questions up until so far?
I think there was one question in the chat earlier. I don't know if you can see the chat.
So if you stick with me to the end of this class, or even to the tutorial for later today, I will actually have a couple of, the last step is not necessary anymore, actually. So this is the response to the specific price vector, but we are going to go through an example or several examples in the exercises. Also considering budget constraints. So we will revisit this type of simple ascending auction that I was talking about. Right? Well, let me maybe just briefly go back. So in here, this is this price vector that emerges from this matrix here. And from this price vector, we get this matrix. This means here we don't have to update the prices anymore. because we can already find a perfect matching. So this is kind of the response to the question in the chat. All right. So let me talk a little bit about this application, because that hopefully provides you with some motivation on the theory behind all of this. And this is, as I said, a market for fishery access rights. A bit of a background, as you might know, overfishing is one of the prime environmental challenges today, right? And in, I think, the early 2000s, there were a number of papers that came out saying that about a third of the fish stocks are overfished, heavily overfished, or have collapsed even. So there was a huge push on policymakers to do something about it. And one of the primary policy tools is cap and trade. Right? This was already introduced for emission trading in the States and in Europe, but it is called catch share system in the language of fisheries. So the idea here is you determine a sustainable level of fish that you can take from the seas every year, and then you distribute shares, and then the shares can be traded. Right? So there was a very nice paper by Birkenbach in Nature in 2017 that showed that the fisheries that actually used catch share system were amazingly effective in combating overfishing. So they could actually regain many of their fish stocks. Right? Which leads to the question, so why wouldn't any fishery industry use catch share system? And the response was given in a commentary by Rosenberg in the very same issue. And he said the allocation of shares is essentially the substantial policy problem here. And he was referring to the initial allocation, the IPO of these shares, if you would like, but also to the regular reallocation of catch shares that always needs to take place when there are changes in the industry and so on and so forth. So New South Wales was a case in point for the second, right? So this means there was a need for a reallocation. Let me describe a bit of a background. This is a fairly large commercial fishing industry, harvesting around 15,000 tons of fish annually, worth around 80 million Australian dollar. And that is at around 2016. At around 2016, there were also around 1,000 commercial fishers and around 100 share classes. So what is a share again? It might be, for example, the right of a business to catch 1 ton of sardines in a region near Sydney, say. Right? So that's a catch share. In similar catch shares or catch shares of the same type would then be a share class. It's a multi-unit market that we designed later on. So between 2002 and 2007, these shares were distributed among the fishers, some of them using a grandfathering scheme, others just evenly among the fishers, right? With the intent at some point, these catch shares would be binding. But that took quite some time. And only at about 2016, there was this pressure, well, finally, these catch shares should take effect. The problem that emerged was that the distribution of catch shares just didn't match the catch in the previous years, right? So there was an almost Piketty-like bias in the distribution that fewer than 20% of the fishing businesses did more than 80% of the catching, right? And in the extreme case where the shares would have been distributed evenly, it would really have cut what the most effective fishers could catch in this market substantially. It would maybe have even ruined the most effective fishers, right? So, and there was a danger that this reform would really jeopardize the whole industry, right? So the Chicago School of Business would tell you maybe, well, just let people trade, and the market will solve this on its own. But Rakesh has already told you, well, many markets need design. And why would this be the case here? Well, first of all, remember there were 1,000 geographically dispersed fishers, so you would have fairly high transaction costs if you had all of them negotiate bilaterally, maybe. Then fishers had a fairly poor understanding of the value of these shares, right? So there was no historical price. So what should you charge? What should you ask for? And ultimately, there was a need for package bids. So, for example, a number of smaller fishers wanted really to exit the market. right? So they had a desire to sell their whole endowment and not just parts of it, which would then render them maybe less profitable than they were already, right? And on the other hand, if you were a very effective fisher, say you wanted to expand your business and catch in a neighboring region, you want to make sure that you are allowed to fish a sufficient level that catching in this new region really is viable. So you had these types of package bids or complementarities on both sides. So the original proposal was by the New South Wales government to do essentially a tender. It was called the buyout option. So the government wanted to buy out via tender unprofitable fishing businesses. And the winners were then essentially forced to either sell their shares to somebody else or they just sunset these shares. Right? And the tender should determine who gets an exit grant of 16 million Australian dollar total. Right. So the problem with this was the sellers didn't really know whether they could sell their entire endowment, and the buyers could not make sure that they win a sufficient number of shares. Right. So that was the key issue here. And that led to quite a bit of uproar. So the media down there, the fishing industry was very concerned. You know, there was quite a bit of a discussion how to reallocate these shares now. Right? That was when we got to talk to the Department of Primary Industries, and they actually asked us to design a market for this, a market where both sides, like the buyers and the sellers, could participate. And we actually got to design a combinatorial exchange or combinatorial double auction where you had buyers and sellers, and they both submitted specific types of package bids, let me say. So, for example, the ones who wanted to exit the market, they could say, well, I want to either sell my whole endowment or nothing. Right? And also the buyers, they could say for a particular share class, I want to win at most X. Right? Otherwise, this is not useful for me. So down there is a URL where you can still find some information. There's a lot of detail that I really cannot talk about here. I just wanted to bring this as a bit of a motivating example to address some of the fundamental design questions here. And the question that I want to address really is the simple economic question: how would you, if you have these package bids now, how would you price the different goods? And I want to start with a very simple example here. So we have two items, A and B, and a package, and we have two bidders. And what you see here in this matrix are their valuations for these individual items or the package. So let me pause here, and maybe you want to think a little bit about how would you set the prices for A and B? Say I'm after well-rationed prices now. I want to find linear and anonymous prices that clear the market. Let me restrict our goal to that. So how would you set the prices for A and B? So the optimal allocation would be to award A and B to buyer 2. That maximizes the revenue of the auctioneer. If you have any suggestions, just type it into the chat. So you might just shoot for a price that is lower than what the winner is willing to pay, right, or equal to, but higher than what the highest losing bidders for A and B has submitted. So for A, this would be 2. For B, this would be 4. So you could come up with a price vector of 2.5, 3, 3, 5, 6. So this is one example. Remember, a valuation price would only be a linear price. So one price for each of the items for A and B. So we don't have a separate price for the bundle yet, right? So if you stick to that, here would be a price vector that at least clears the market, right? So the losers would know. So all of those are losing bids, obviously. And they would know why they lost, just looking at the prices. and the winner can still afford this price. Now a somewhat more involved example, and again want to give you a bit of time. How would you set linear prices for A, B, and C to clear the market here? So this is a somewhat restricted view. As you can see, we only have three items here, but the bidders are not interested in the individual items. They're only interested in these packages. Say buyer 1 would be interested to win A and B for a price of 30. That's how to read this specific example. And again, the welfare maximizing allocation is the one with an asterisk. This, if you award A, B, and C as a package to buyer B3, then this would be the revenue maximizing allocation. And here we have one seller. $15.33 times. All right. But if you take 15 times 3, then you're at 45. So this is more than what the winner is willing to pay, right? Any other suggestion? So 13.3, also a good suggestion. But for example, this one, the specific bid would now be paradoxically rejected, right? So because 2 times 13 is 26.6. So here we have somebody who is willing to pay 30, which is more, but he's losing. So you already nailed it, right? So there is no way with these types of package bids to get to linear and anonymous prices here that will clear the market. With the simple, and we are not even talking about competitive equilibrium here, but with the simple requirement that the losers should know why they lost and the winners should, get a price that they can still afford. Right? And that goes back to an example that Ricky already showed you. And we will then dig a little deeper on why this is the case. But this is a market where you would need nonlinear and personalized prices. Right? So if you, for example, were able to charge this one bidder here, say bidder 2 for B and C, a price that is more than 30, and at the same time charge a price for this package A, B, and C to buyer 3 that is less than this 41, well, then we might clear the market. The situation is even trickier, and that's something that we haven't discussed so far. Now, consider that you don't only have one seller, you have 3 sellers. So suppose there is a seller for A, a seller for B, and a seller for C. How would you set the prices now such that we get a stable outcome? Any suggestions? All right. So if you look at the price vectors in the chat, so say we have this 41 here, right? So this is the winner. Now, if we have 3 sellers, he would essentially, we would need a price that is 13.3, say, but that would not be enough. So because then, say, bidder 1 could deviate by talking to A and B, the sellers for A and B, and say, well, I'm willing to bid a little more, right, than the current market price, right? So, but if I'm awarding A and B to buyer 1 now, then this buyer could pay 15, say, to both of these sellers, right? or he could pay one a little more and the other a little less. But one of those bidders would, one of these sellers would receive less than 15, right? Or 15 at most, right? So this means buyer 2 could now speak up to this one buyer. So if we assume that the seller B receives 15, he could say, well, I promise you 16, and talk at the same time to the seller C and promise him, say, 3, right? So then both of these sellers would be better off and this buyer would be better off. Understand? And you can obviously rotate and do the same game. If you now award this package B and C to B, then another combination could deviate. So this is one of these examples that Rakesh was describing as the core is empty. So there is no stable solution, no stable price equilibrium. And that's something that happens or can happen in these combinatorial double auctions. Right? So 2 insights that you might want to take from this. First, competitive equilibrium prices need to be nonlinear and personalized. You knew that already from prior classes. But second, the core can even be empty in these two-sided markets. Right? So in the sense that we might not find a stable outcome. So let's get to some optimization models here. So one way to write up this winner determination in such a double auction here, and I think it makes it easier to digest. I took apart, or I'm looking here at a market which is really a double auction. So I have a predefined set of buyers and sellers. Sometimes you have exchanges where bidders can be both, or participants can be both. So here I distinguish between buyers and sellers. So in the objective function here is simply I want to maximize gains from trade. Right? So this means the left term here is what the buyers are willing to put on the table. So what the buyers are willing to pay minus what the sellers are asking for. Right? So and X and Y is essentially the vector notation for the packages S and that buyers are willing to buy, and Z for what the sellers are selling, right? So I distinguish this in the notation here. Then we need a demand supply constraint. So what I'm putting on the market, and this for each item is what I'm selling. So I can't buy more than what is sold, obviously. Right? And then we have an XOR constraint here for the buyers and the sellers. So we assume that they submit a bid for each and every possible combination, and they can win at most one of those bids. Right? And this is written up as binary programming. So fortunately, Rakesh was already giving you this great introduction. So what is next? You've already seen that for combinatorial auction. So here, this is the extended program that you can write up for this combinatorial double auction. Right? And there are various extended formulations, I have to say. Not all of them are integral at the end. So this is an extended formulation that is indeed integral. So I'm using the same trick here, and I think this goes back to Bichler and Ostroy, and there's a very nice paper by Sven and Rakesh who used very similar formulations. So this is just the same environment, but in a double auction environment, very much like our Fisher market. And again, what we use here is a variable delta xy, and this is a variable for each and every possible allocation. Again, this is going to be a huge, huge integer program, right? So the point we want to make here, so this is for theoretical purposes. You would not necessarily write it down like this. But if we have a variable for each and every allocation, then essentially at the expense of the size of this program, we would always get an integral solution. And this is kind of easy to see because we can, these are weights here, and the sum of these weights need to be 1. So essentially the optimization would always pick one of the allocations that maximizes welfare. So it's the same objective function, maximize gains from trade here. And if, say, we have a tie, well, then you can always find an integral vertex, meaning one allocation that really maximizes welfare. Right? So, and we have now another set of dual variables here. So the prices for sellers and buyers, PIS buyers, PJZ the sellers, and then we have the dual variable that constrains every buyer to win at most one of his bids. So the dual can again be interpreted very much like what we've done in the assignment market, is the payoff of this buyer, and similarly the payoff of the seller, PJ. And then we have yet another constraint. And here we have a dual variable that we call pi A. And this is essentially what the auctioneer makes or can be interpreted, or how much he subsidizes the market. And we will see that this dual variable plays quite a bit of a role in these double auction markets. So this is just the dual of what we've just seen, and very similar to what we've gone through at the beginning when we looked at the assignment market. We can now look at dual complementary slackness constraints. So this is what we have down here. And we have a very similar nice interpretation. So just take the very first dual constraint here. This leads to this new dual complementary slackness condition, same interpretation. If XIS is 1, then this constraint needs to be tight. So then this means the payoff is the valuation minus the price. So we maximize value minus price. Same thing for the sellers. And then we have this constraint down here. So this is now interesting. So what does this tell us? Any thoughts? Well, it's budget balance, right? So what the price of the buyers minus the sellers, this needs to cancel out, right? So if we pick a particular allocation, then we have budget balance, except for this pi A, right? So this now, let me maybe not get ahead of myself here. All right, so this pi A now makes a difference. So let me maybe jump to this. So first of all, what is a very easy lemma here is saying, well, if D admits an optimal solution and pi A is null, right? So this is just null. Well, then we actually have budget balance. Right? And that also leads to this proposition here that the assignment X and Y stars, the optimal solution of the primal and the dual, form a competitive equilibrium for the model if and only if pi A is null. So I should maybe mention the competitive equilibrium conditions for these two-sided markets, and this is something you can read up in the literature, is at those prices that I'm going to set, so pi JZ and pi IS, each of the participants maximizes his payoff and the budget is balanced, right? And this is exactly the case when pi A is null. So now remember the one example that I showed you where where we didn't find a core stable solution. Let me maybe just go back. This one here. What do you think would happen if I use these numbers and plug them into the formulation that we just had? Well, actually, pi A would not be null. So you could now say, well, I want to have budget balance. I want to enforce pi A is null. Well, then this whole theory breaks in a way. So I don't get integer solutions anymore. I get fraction solutions. So this is essentially how these things connect. So this is essentially an easy way to check whether the core of such an exchange market is empty, whether I can find a solution that is core stable or I cannot. I just check whether pi a is null, and if you set it to null, would I get a fractional solution or not then? All right. So I was already talking about the core quite a bit. You are already familiar with this since Rakesh has introduced it. So these are again the core constraints, right? So we have core efficiency and core rationality. So essentially, there must not be a subset of the participants of this market that can deviate. We've seen that the example that I was just showing you again, this was an example where we had an empty core. And let's now see how all of this connects. So you see here this core efficiency constraint. One of the things that we can do is let's now look at the objective function of our primal and say we solve this to optimality. Then Vn is all right, so I mark this with a star. So this is the optimal allocation. So this is just our objective function, right? And now what we can do is if we have budget balance, we just add a set of terms, right? So we can do all right. So we know if you have budget balance, this cancels out. And this is nothing else but so these are all the same. So this means if pi a is null, well, then we actually have a core imputation. So I've just shown you that core efficiency holds, right? And with a similar argument, you can also show core rationality. But this is how it all falls in places. So we have these core solutions if and only if pi a is null, right? And I've just shown you a case where this is not feasible to find such an allocation. Are there any questions at this point? So maybe one comment regarding incentive compatibility. We've only been talking about competitive equilibrium now. So you might remember Rakesh was telling you about additional assumptions that we need such that we get the same properties as in the assignment market, where the victory outcome is in the core, and as a result, we get by such an ascending procedure, for example, for a combinatorial auction, we actually do get incentive compatibility or strategy improvements. So very strong. We satisfy a very strong game theoretic solution concept. Right? So you could do the same thing here. The problem is in these double auctions, if you use a VCG auction, then budget balance breaks. Right? And that's also a very well-known problem. So you can, you achieve incentive compatibility, but the auctioneer actually makes a loss. Right? And in general, and I don't want to spend a lot of time on Myers and Satterthwaite, which is a very fundamental result in this overall field, with double-sided auctions, to get all of these design desiderata together that I was showing you at the beginning is way, way harder, right? So by and large, I'm not, in this class, I'm not talking about incentive compatibility anymore. Let's assume for a minute, this is a large enough market and bidders are price takers. Right, so far so good. Let me get to Friedrich Hayek here, who was a Nobel Prize laureate and an advocate of the price system. And he has written extensively about prices. And one of the quotes from his book, The Price System as a Mechanism of Using Knowledge, says, the most significant fact about this price system is the economy of knowledge with which it operates, or how little the individual participants need to know in order to be able to take the right action. Right? And I think he goes on and essentially says it's super effective because you need to know only these few prices, and then the market would form and would ultimately find a welfare maximizing outcome. Well, if we have these non-convexities, I hope what you've learned now really is, well, these bidders in these non-convex markets would need to know a lot, because if you have nonlinear and personalized prices, well, this means we have an exponential set of these prices all of a sudden, right? So things are getting way harder. This is what I want to say. Right? So this was a bit of theory. What would it need to take in order to get competitive equilibrium on these markets? So this is what I hope we have understood now. You can imagine that we did not get very far in explaining the theory to the Department of Primary Industries. What do you think were the requirements that they wanted to have enforced? What type of prices did they wanted to have? Any ideas? So what would matter to a fisherman? They were actually talking a lot about fairness. They wanted to have fair prices. So you could now say, well, actually this type of prices that I've just been showing you are fair because they're envy-free, right? And that's one of the nice things about a competitive equilibrium. It essentially describes envy-free prices, and envy-freeness is essentially a standard way to describe or examatize fairness in economic theory. But they had a very different understanding of what fairness means. So it means that it meant to them, if two fishers sell the same package, they should get the same price. Right? And that, in a way, sounds very intuitive. There is even a concept in marketing that talks about price fairness. It says, well, if two people buy the same item, say, they should have the same price. Right? And that's considered fair by many, which is slightly different to these envy-freeness concepts that we often use in economic theory. Right? So we are essentially back to linear and anonymous prices. All right? And the question that you could ask now, okay, so let's just go with linear and anonymous prices. So what would happen? What would be the problem? And obviously they have these nice properties. So bidders achieve the same price for the same package. They are very simple, and it's only a linear number, right? So if I have 100 share classes, it's only 100 numbers, and not to the power of 100, which is a very, very large number, obviously. Right? So what is the problem with these linear prices? The first and the most obvious one is it might come at efficiency losses or welfare losses. So how is that? Here is the most simple example I could think of. Say I have a seller selling a package of two objects, right? This might be two shares. Then I have one buyer who is willing to pay $10 and a second buyer who is willing to pay 26. So in total, there would be gains from trade because the buyers in total would put $36 on the table and the seller only asks for 30. But if I enforce a linear and anonymous price, well, then I cannot charge more than 10 because buyer one just cannot or is not willing to pay more, and then there would be no gains from trade. All right. So problem number one, we have an efficiency loss. Right? Let's first talk about this problem. So how severe is this problem? And first thing we did is, well, let's take this worst case example that I was just showing you, right? And this is a somewhat more involved proof where we actually draw on order statistics. But essentially what we do is, suppose you have a multi-unit market with one seller selling a package of K units, very much like in the example that I was just showing you, and N unit demand buyers, right? In the previous example, we only had 2, it might be N, right? And the valuations of buyers and sellers are drawn from the same distribution. Then we can bound the efficiency loss by K minus 1 divided by N plus 1. So K is the size of the package. So if the size of this package packages that are traded gets small, well, then the efficiency loss is small. Or N is the number of bidders. If the number of bidders grows large, then the efficiency loss grows small as well. Right? So this is kind of intuitive. Rakesh has yesterday been telling you a little bit about this Shapley-Forkman lemma, which is another way to spin the story, which essentially says, well, if you have many, many small package bits, kind of the Minkowski sum would convexify, right? And what we did here, we were fortunate to have very detailed data about what the individual fishermen possessed. So we could do very realistic simulations. And we ran simulations before we ran the market to understand how big would the efficiency loss be, right? And we had, say, 20% of the fishermen participate up to 100% of the fishermen. What we see up here is the average efficiency in, 50 or so different iterations of these markets, right? And you see that the efficiency loss grows smaller and smaller. So if you have, say, 60, 70% participating, it's maybe in the order of 7, 8%. That was considered totally acceptable as long as they had fair prices, right? And finally, we decided we go with these linear prices. Right? So let me add at this point, this is not so unusual. If you look at, they had electricity markets nowadays, they do the same thing. So they actually charge linear and anonymous prices. It comes at some downsides, but this type of fairness that the fishermen down there in the Department of Primary Industries were after. So this is something that apparently is relevant in other markets as well. And to cut the long story short, obviously, if the non-convexities are huge, say your integrality gap is very large, well, then these linear prices might be very far away from what you want, right? But if the non-convexities are not so big, or you have many, many players, well, then, also the efficiency loss might be okay. Right? Efficiency loss is only one of these aspects that we might want to consider. The other is something that we have already discussed in our toy example, namely paradoxically rejected bids. So suppose we have here one seller who is selling 3 items A for $60. He's selling the package. And we have 3 bidders. They are all willing to pay up to $30. So obviously, if they trade, there is significant gains from trade here, right? And then we also have a seller who is selling only 1 A. Okay, so what happens here? So if we have these guys trade, well, then we can set prices arbitrarily. So as an example, I had here 25. So then the seller, he would get 75. He only wants to get 60, so he makes a gain or a payoff of 15. And each of the buyers is willing to pay 30. He only pays 25, so he also has a payoff. Things are fine. But now look at this second seller. So he is only selling 1 item, and he's only charging 10, right? So, well, in this case, he would have charged less than what the market price is, and yet he's rejected. He does not get to trade, right? So this is what is known as a paradoxically rejected bid. These types of bids happen in the fishery market, and they do happen in certain types of electricity markets. So this is something you need to take into account, right? It's another price you pay for these simple prices, let me say. So I see now there was another question. So the fishermen care not only about their own price, but also those of others. is the question. Well, this was really, we were telling them about this impossibility of these linear and anonymous prices. And said, well, you need to price differentiate here. And this type of envy was very natural. And if you think about it, people don't know the values of the others. So the only thing they can really observe are the prices, right? And that's what they can compare. And if your next door neighbor sells the very same package and he gets way more than you do, well, that might lead to some discussion, right? That needs explanation. Right? So it's a trade-off, what you want to achieve and what axioms you want to satisfy with the market design. Right? Did that answer the question? If not, then please ask. All right, so let me get to an end of this fishery story. This turned out to be a very large mixed integer program. I want to be a bit faster here because I need a bit more time for the rest of this class. But you know, we used all types of mixed integer programming tricks, Bender's cuts and whatnot, and we could actually solve the problems to optimality on a compute cluster. We were very happy about it, and so was the minister down there. He wrote us a very nice letter, and overall we had close to 600 commercial fishers participate, which was way more than they expected. We placed 740 buy bids, 430 sell offers, and 107 very large exit package offers. And in total, 36,000 shares were traded, and 86% of the buy bids were matched, which was, I think, a very good result. Right? So this is just to give you a bit of a sense that these types of theoretical considerations do matter in real-world market design. Let me get to another topic that is close to my heart now, unless there are any immediate questions. And this is budget constraints. So I've been involved in a number of different market design projects. In budget constraints almost always mattered. So the example that I gave you earlier was spectrum auctions. So I've never seen a spectrum auctions where there wouldn't have been budget constraints on the bidders. So it's essentially a fixed cap, and the buyers must not bid more than this cap. This is a bit different, let me say, than what has been shown to you in this model by Quincy that Rakesh illustrated, where they also had budgets. But this, what we are talking about here, is a hard budget constraint. Right? So even if you earn money, you must not spend more than X. All right. And this is very, very natural in many markets. It was also an issue in these fishery markets. And in these fishery markets, we kind of ignored it. We actually had a subsidy, different story that I don't want to go into. But we were thinking about, so how would we model this market if we actually take these budget constraints serious? Right? So here is a little question to you. Suppose, I think by now you know this notation. These are the valuations of the bidders, and now we add these budgets. So how would you set prices now? Obviously, the welfare maximizing trade would be we assign the package A, B to buyer 1, right? This is more than the alternative allocation would be this one here, right? Where we sell A to buyer 2 and B to buyer 3. So if we want to enforce the welfare maximizing allocation, how would we set prices? So if you look at this example, 2.5 and 2.5, right? So this is something that bidder 1 cannot afford, right? So he only has a budget of 3. So, and that's the problem here, right? So if you have budget constraints, you know, this cuts into the welfare maximizing allocation, right? So essentially, a core stable outcome would be to assign actually A to buyer 2 and B to buyer 3. And then each of the sellers would get a payoff of 2. And this buyer with this very high value, you know, he could not jump in. He could not become winning at those prices, essentially. Right? So you might have to live with a welfare loss, which is not so too surprising. Right? But there are also cases where if we don't have budget constraints, there is a solution in the core, but with budget constraints, there isn't. Right? So if you look at this example, it's fairly easy after the example that we already did to find a price here. So we have, for example, a price of 4.5 and 4.5, and this is still something that buyer 1 could afford here, right? So at a price of 9, he could afford this, and none of the losing bids would win. But now, if we add a budget constraint, we again run into some issues here, right? So think a little bit about this. But the problem is that with adding these budget constraints, the core is empty in this example. Think a little bit about why this is the case. So there are these two possibilities. Either you assign the object A and B to buyer 1, then in total you cannot charge more than 3. Right? But then these bidders can jump in. Writing buyer 1 would buy both for 3, or buyer 2 gets 1 of 2, right? But then always, if you charge 1.5 or so to one of the bidders, then buyer 2 can make a deal with the other seller, right? So also in here, maybe it's easier if this is shown explicitly. If B1 obtains the package here, then we could charge, as I said, only 3. And B2 can always approach one of the sellers and offer more than B1, right? That's the point here, right? Because at least one of those would have less than 1.5, say. And if we assign one of the goods to A, say, well, then bidder 1 could approach buyer A and pay a bit more than 2, which is the budget constraint of buyer 2, and an epsilon to seller B, and they could deviate. So no matter which allocation you choose, there would always be a deviation. So takeaway, again, is even in cases where there would be a core allocation without the budget constraints, the core can be empty with budgets. Was that clear? All right. Right, so then we started thinking about, well, how would we compute prices here? And the key issue is if you try to write this up as an optimization problem, you somehow need to take the budget constraints into account when you determine the prices, right? And that's what actually makes it a bit challenging. Because so far, we first solved for the welfare maximizing allocation. And in a second step, we looked at the duals and determined the prices. So now we have to consider the budget constraints when we allocate. That's what you've seen in the examples. So this means we need to do pricing and allocation in one step. Right? First, the somewhat surprising result might be this is a problem that is super hard. So this is a problem that is sigma to p complete. So this is one level up from NP in the polynomial hierarchy. Right? So I'm not going to have time to go into the proof, which was very lengthy, but it essentially reduces from Q set, very much like in P. Set is the central problem. Quantified set is the central problem in the second level of the polynomial hierarchy. And it would be, would have a, the question that we ask for this satisfiability, this Boolean formula, phi here is there an X such that for all Y, this Boolean formula is true? So that might not be totally obvious, but if you try to write this up as an optimization problem, then you at least get a bit of an intuition. And as I said, what you need to consider is a budget constraint here. So again, the objective function is what we had so far. We maximize gains from trade, what the buyers put on the table, minus what the sellers want. So that's what we want to maximize. And now we have various types of constraints that you've already seen. Say each bidder must only win one of his package bids, say, and we cannot buy more than what is being sold. So demand supply. So I'm not listing these. But what is new here is we need to make sure that the prices that are being paid are less than what a buyer can afford, less than his budget constraint. Right? And we want to have the prices be core stable. So essentially, we could now check against each possible coalition. Right? So each possible coalition would be, what is written up here is essentially another optimization problem. Right? So for this specific coalition, and there are exponentially many, you would need to solve this problem again. So this would be a very ineffective formulation, right? We have a much more lenient and parsimonious formulation that is much more effective. But conceptually, this is how you might want to start thinking about this, right? I want to find prices that are core stable. So they should be such that no core coalition can deviate. That was the very definition of the core. And at the same time, they respect the budget constraint. And from this set, I want to now find the welfare maximizing allocation among all the ones in this set. And this is a problem that is sigma to p hard. Actually, this general class of bi-level integer programs, when the lower level programs are also non-convex, these are also known to be sigma to p complete. And that goes back to a proof by Yaroslav in 85. So this is a bit of a bummer, right? So at the beginning, you remember I was telling you about these welfare theorems. This is essentially giving you some idea that markets can solve distributed resource allocation problems. Now I'm adding some non-convexities, and in particular, I'm adding these budget constraints, these quasi-linear utilities, and all of a sudden the problems become really intractable. So if you're on the second level of the polynomial hierarchy, problems are really difficult. So you know that many problems that are in p-hard, for realistic problem sizes, we can now solve them, right? With the advances in integer programming that we've seen, bi-level integer programs are way harder, and we spend considerable time to understand how hard they really are. And I want to give you a couple of numbers now to give you an idea. So first of all, this is the number of coalitions that would matter. So if you have 5 buyers in this market, the fishery market, 5 sellers, and you allow for all possible coalitions, we have 960. With 10 buyers and 10 sellers, we are already at 1 million, right? Only coalitions. What we can do is we can restrict the size of the coalitions that we consider. Well, then obviously it's less, but by and large, obviously the number of coalitions grows very, very strongly. Then we actually implemented this. So we wrote our own bi-level integer programming solver and tried to understand what are the problem sizes that we can reasonably expect to solve. So with say 5 sellers and 5 buyers here, we could actually solve out of 8 instances, all 8 instances. Right? But if we increase the problem size by a bit, say we go to 10 buyers and 10 sellers, we could solve none of those in a particular time frame. So we didn't let the solver run for ages, but we gave it, I think, an hour or so. Right? So really the problem explodes on you very, very quickly, right? And that's kind of the characteristic of problems in this complexity class. So the one thing you can do is you can still, again, restrict the number of the size of the coalitions. Why would that make sense? Well, obviously, if these problems are so hard, it might also be very hard to form a useful coalition, right? So maybe if you restrict stability to coalitions of size 3 or 4, that might still be good enough for reality. Maybe forming a coalition of all close to all possible bidders might not be tractable anyway, right? And then if we use that, then we can solve much larger problem sizes here. So with, for example, 10 buyers, 5 sellers, we can still solve all the problems in our instance set. Right? So this should just give you a bit of an idea. What does it mean when I talk about empirical hardness here? So one idea could now be, well, you've just told us in the original problem, or very often, you just ignore these budget constraints, right? So maybe this is not that bad. Maybe very much like what you did with the linear prices, simplify the problem. Maybe what you get is not that bad, right? Unfortunately, that is not true when we talk about these budget constraints. You rather not want to ignore them. So we essentially did some computations for small markets where we could still solve the optimal solution, right? And you might want to take a look at this column here. This is the efficiency losses that we got, the welfare losses. And you see that in most cases, they are really substantial. So I should explain maybe here that we simulated bidders that did not bid their value, but their capped valuations. So their valuations capped by the budget, right? So if you had a value for a particular package of 100, but your budget is 80, well, then you only bid 80, right? And you essentially pick the wrong allocation if you ignore this, right? So you get a very different allocation, obviously, if you have budget constraints and valuations than if you only take a look at the budget capped valuations. All right, so are there any questions on this?
I would have one, Martin.
Yeah.
The tables that you showed with the large running times, I don't know whether I got it right. Is this for the bi-level integer program?
Yes.
How did you solve it?
I mentioned it briefly. We've developed our own solver. So there are essentially algorithms, and it's you kind of, it's branch and cut type of algorithms where you fix particular binary variables and then branch again. So I can point you to a number of papers. So there are different approaches. Bi-level. So let me put it that way. Bi-level integer programming has become fairly popular in the recent years. So there is a new paper by Fischetti that just came out, I think, 2 years ago, and so on and so forth. We've used a paper by Zhang, which did have less restrictions on the linkage variables. So the linkage variables are, in our case, the prices that we have in the upper and the lower level programs. Yeah. And that's why we choose that approach. I'm not claiming that this is the most effective and efficient solver. We just wanted to demonstrate, so how hard is it, empirically speaking, to solve these types of problems with one solver. You don't get this commercial off the shelf. At least I don't know of any commercial off the shelf solver for bi-level integer programming problems. And it took us quite some time to get this implemented, I have to say. Yeah.
Okay, thanks.
So maybe last point, I think I have 5 more minutes, no, Sven? Yeah. So this is a bit of a bummer if you think about it, right? So again, if you add this kind of really real-world design desiderata and constraints that you have in these markets, then it might get really intractable, right? Or you can really only solve very, very small markets. So what you can think about next is, well, why don't we restrict the types of valuations? This is a trick that is being played in algorithmic game theory all the time, right? So if we can't, get to tractable solutions with all types of valuations, maybe restrict the types of valuations to some extent. And this is what we did more recently. Well, why don't we look at the assignment markets again? We don't allow bidders that have general valuations, but just ones that have unit demand. And now we are back to the very early slides that I was showing, right? So the assignment market rate. So maybe we find polytime algorithms to compute the welfare maximizing core stable allocation for this simple assignment market. So this would be a simple example here. So we have, again, a buyer. How to read this is a budget of 2. And the second buyer has a budget of 4. We have 2 sellers. They have an ask price or a reserve price of null. And these are the valuations. So buyer 1 values the good of seller 1 at 4 and the good of seller 2 at 10. Right? So there are two possible allocations, as you can see. The first is the solid line. We assign seller 1 to buyer 2, seller 2 to buyer 2, and seller 1 to buyer 1, or the dashed lines. And obviously, the dashed line, this allocation is the welfare maximizing one, because we would have a welfare of 13. All right. So can we enforce this? Very similar to what you've seen before. Not really. You don't find a core stable outcome that would, be the welfare maximizing outcome as well. Right. So simple example: say you charge a price of 3 for seller 3, because this is how much buyer 2 is willing to pay, and then we charge a price of 2 because for item 2, because this is the budget constraint of buyer 1. Right? If we do that, well, then we have a payoff of 10 minus 2 is 8, 3 minus 3 is null, and 6 minus 2 is 4. So it's pretty obvious that this would not be core stable. So this buyer would rather actually get at those prices, would get the item of seller 2. And similarly, seller 2, he can only charge 2 for buyer 1. He would also, I'm sorry. Here we are. So similarly, seller 2 can only charge a price of 2 from buyer 1 because this is budget constraint, but he could charge a much higher price from buyer 2. So at those prices, and this is as much as I can charge, both buyer 2 and seller 2 would want to deviate. All right. So that shouldn't come as a surprise. So what we show is actually that, first of all, there is no incentive compatible mechanism that terminates in a core stable and welfare maximizing solution for every input. And second, that if we allow every input means all possible unit demand valuation. Right? Well, then computing a core stable welfare maximizing outcome is NP hard. So remember, this was in P before without the budget constraints. Now we are in P. We want to select the welfare maximizing outcome, be in the core and respect the budget constraints. Now we are in P complete. So let me give you maybe a brief intuition on why that is the case. So here is a simple example with 3 bidders, and they have a value of 10 for either the apple or the banana, and they have budgets of 1, 10, or 2. Right? So there is a bit of literature in this, trying to find core stable outcomes with budget constraints markets. And they often draw on variations of this Hungarian algorithm that I was showing you at the very beginning. And how would this Hungarian algorithm work here? So we would again start at the price of null, and then these bidders, they would reveal their demand set. Right? So we can increase the price, they would again reveal their demand set. And now, importantly, we are at a price of 2 and 2. This is when bidder 1 drops out because we've reached his budget constraint. So now take care. Why would I know that this is the budget constraint of the bidder and not his value as an auctioneer? This is not super obvious at first sight. So in the standard Hungarian algorithm, what you assume is that if you reach your value, you're indifferent to the good, getting the good or getting the empty set. So your demand set includes both. Right? If you hit your demand set, your budget constraint, well, then this is not true. Then you in this round, in round number 1, he reported the banana, and in the next round he reports the null set. There was no round where he reported the banana and the null set, right? And that's how I can distinguish between those two states. If I couldn't distinguish between those two states, I'm doomed anyway, right? But now that I can, at least in theory, distinguish between these two states, I know that he hit his demand set. Well, if it's only this one guy, it's actually not that bad. I can just remove the item from his demand set. I go back to the last price vector that we had here, look at the allocation again, or the demand sets again, and now I find a perfect matching. So each of the remaining bidders gets one of the items, right? And I'm done. So actually, as long as I only have this one item, a bidder who hits his demand, his budget constraint, then I actually have a core stable solution, which is interesting. So, but now consider we have a copy of this guy. We have two, and for some reason they hit the budget constraint at the same time. Well, then as the auctioneer, I don't have enough information to decide. I might pick the first one, but the second one has a way higher valuation, right? So I cannot guarantee welfare maximization anymore with this simple algorithm. Right. So this is kind of what makes it a bit hard. So if I have a restricted set of valuations, let me say, then such that in no round two bidders hit their demand set at the same time, their budget constraint at the same time, I'm in good shape. Then I actually have a polytime algorithm that is even incentive compatible and picks a core stable and welfare maximizing outcome. But if this happens, then there's not much I can do. And this is essentially what we show here. So let me speed up here a little bit as I'm reaching my time limit, I think. But essentially what we show is that in assignment markets with payoff maximizing but budget constrained bidders, there is no incentive compatible and budget balanced mechanism terminating in a core stable solution for every input. And every input would really not rule out the case where two bidders hit the budget constraint at the same time. So what can you do? Well, let's ignore incentive compatibility. You can then write up the allocation problem as an integer program again, right? And let me not go into the details, but this, what you see up here, is your standard, almost your standard assignment problem. And then I add these two constraints, which enforce stability. These are core constraints, essentially, right? And with these core constraints, I can actually compute a core stable outcome that actually maximizes welfare. The problem is that you can show by reducing from maximum independent set that this is an NP-hard problem. All right. So I would have loved to spend a bit more time on this, but I think I'm already running over. Let me maybe get to an end, and then I'd be happy to take questions. So what is the take-home message from this first class? First of all, most real-world markets have complex constraints. I hope I could convince you. I was showing you this fishery example, electricity markets, industrial procurements, transportation tenders, they all have these characteristics. So we ultimately have non-convex optimization problems. It's, I think, really important to understand how we do pricing in these non-convex markets. And if you look at standard competitive equilibrium theory, it provides fairly little guidance, right? For example, if you really dig into electricity market pricing, there is a lot of heuristics, but there is it's far away from a complete theory, I would say, right? And ultimately, it's very close to IP duality, which is, as we all know, a hard thing, a hard nut to crack. So we need to extend the theory and take real-world constraints into account. And I hope I could convince you that, in particular, budget constraints are a beast and are very hard to come around. All right, so this is it for the first class. For the next class, then after the break, we'll discuss smaller markets where we look at Bayesian Nash equilibria, very different subject. I'll be happy to take questions if there are any. I actually see in the chat one question that I didn't answer from yes, but so I guess I was getting that usually we say the utility of losing is usually null, and winning bid is based on the bidder's own utility function. Now that would include not only the price the bidder paid, but also that of the other winners. Well, it does. Yeah, it's a good point, right? So the way we model this is not necessarily that it what the others, that you have externalities, that the price of the others would really have an impact on your utility. We just try to enforce this as a constraint that everybody gets the same price, right? But yes, I mean, independent private values are strong assumptions, and often you have externalities of the sort that you mentioned. So essentially, it's just a constraint on the type of price function that we want to compute. Right? That's how we model it. We don't necessarily have different assumptions at this point on the utility functions that we assume, other than that. I hope you could recover from the first part. So the second part of this class is a bit different. So remember, in the first part, we focused on competitive equilibria, and this is very much in the tradition of competitive equilibrium theory, general equilibrium theory. And one decisive assumption is really bidders are not strategic. In the 60s, I would say, people started asking, well, you know, bidders are strategic, so you need to take a way more game theoretical look at markets, right? And that's what we are going to do now. And we talk about, at the beginning, very simple auctions. So selling one object. And I'm lucky that I'm the last of the speakers because I can draw on a lot of material that you've already learned about, like standard auctions. I don't have to explain anymore. But you know what people in the early 60s, most notably William Bichler, who got the Nobel Prize in '94, looked at were really very simple single object auctions. No computational complexity in a winner determination. It's a simple sorting problem that you have to solve, right? And the questions that they were asking were slightly different. So suppose we look at these very simple auctions, as you can find them in practice. There are different formats, and what are the pros and cons of these formats? So we have an ascending clock auction, we have a first price sealed bid auction, so everybody submits a bid in a sealed envelope, and then the auctioneer picks the highest. We have the second price auction. You've already heard about the Bichler auction, which has dominant strategies, and we have the descending Dutch auction. And so, how can I compare these, and how can I model these formally? So what is the right way to think about these auctions? And I mean, since you already had this class on revenue maximizing auctions, this is all well familiar to you. And you've also learned that the Bichler auction has these dominant strategies. The ascending clock auction has these strategies as well. But the first price sealed bid and the descending auction don't, right? And the solution concept that is being used in order to model and understand strategic behavior in such auctions is that of a Bayes-Nash equilibrium, right? And that's what this class will be all about, right? And early insights actually go back to William Bichler's original paper in '61, where he essentially showed us how would we model, how would we get to an equilibrium in a model where we have auctions with continuous type and action spaces, right? So you have bids on the real line, right? So you can submit any type of bid, and you have competitors. So these are the types, and I get to that in a minute, that are drawn from some continuous distribution. Right? And that's how would you find equilibrium in such an environment? And that goes back 60 years. So let me first introduce what a Bayesian game is. So it's a quintuple. We have bidders, calligraphic eye, as in the first class. We have now actions and action profiles. So this is the set of actions of bidder one. And think of it now as the possible bids of bidder one. And then we have B, which is the type profiles. So bidders are modeled as types that are drawn from a particular distribution here. Right? And then we assume we have a prior distribution. And this prior distribution tells us how likely it is that I encounter a particular type of opponent. And then we have utility functions that can take on various forms. So usually we will work with a standard quasi-linear utility function. This means our rho here would be 1. So it's really just the valuation or type. Consider these for now equivalent. These terms are synonyms. Times xi, so this is, would I be awarded the item or not in this auction, minus the price for this item. Remember, we are at least here now in single object auction. And you can come up with various other types of utility functions. So if I deviate from rho is 1, you can model risk aversion or risk-seeking behavior or whatnot, and you could even think about loss aversion. You're in general very free about how you choose the utility function. But standard auction theory or auction theory 101 would mainly assume standard independent private values. So these types are drawn independently of each other, and quasi-linear utility function. But these assumptions are relaxed over time. Right, then the auction determines this allocation, and beta star will now describe our base Nash equilibrium. And this is going to be a function, right? So a function that tells me for each possible type that ex ante, before I even know my value, it would tell me for each possible type that I can draw, or each value that I could have, which bid I should submit in a particular first price seal bid auction. Any questions here? All right. So let's take a look at the standard first price seal bid auction in this model, in this independent private values model. And think a little bit about how we would derive a proposal that's not yet approved for such a base Nash equilibrium strategy. And that is really taken from standard economics textbooks. So as you've seen, we have this prior distribution F. Then Y1 denotes the highest among the n-1 remaining bidders, right? So let's suppose the bidder that we are concerned with is bidder 1, and we are interested in all the other bidders, and we take the second highest order statistic, right? From a particular draw from this distribution that we're given. So the distribution function for this random variable y1 would now be this one, right? So again, we were interested in the highest of the remaining bidders. And now what we can do is we can write up a utility function, right? So first note that when would a bidder win? Well, if the bid of the highest opponent, the bidders that are not one is the one that we're considering, the highest opponent's bid would be less than PP is the bid that I submit. All right. So now we can rearrange terms. So we are looking at, let's go here, 1 second. Hit this now. So this is the maximum of the other bidders' bids. So we can rewrite this as beta of y1, right? And so this means beta, and we assume there is a symmetric equilibrium function of y1 is less than p. And we are interested in that probability. Now we take the inverse of this bid function, and this results in y1 needs to be less than the inverse of the bid function of my price p. Right? That's another way to write this down. So essentially, what and the right-hand side here is just my value, right? It's the inverse of the bid function of the price that I'm going to bid. That is my value. Right? So with this, I can write up a utility function like this, an expected utility function. So the probability of winning and at a price p times the payoff, which is again v minus p. my value minus the price. All right. So with this utility function, expected utility function, I can now just go there and do the usual. I take the first order conditions. I want to find the optimum of this expected utility, right? So that needs a bit of calculus. So I need to take the derivatives of this part here. So for this, I need the chain rule because I have this nested function here. And for this, I also need the reciprocal rule. And what it would give me is essentially this here, right? So, or if I take the first order conditions, so this is essentially the term that I get, and I set this now, standard way. I want to maximize the expected utility. And now I make an additional assumption, right? And this additional assumption is symmetry. So this means all bidders play the same equilibrium bidding function. So my P is nothing else but beta from V. So beta, since we're all taking this, using the same betas, the same equilibrium function of my type V, that is the price that I'm bidding P, right? So now I can just replace this by V, right? So I rearrange terms, use again the inverse of the bid function, and then instead of this, I enter V. Instead of this, again, I use V, and so on and so forth. Right? And well, now I can just multiply this by the derivative of beta. This is what we had. This is what we would get now. And if you look at the very left-hand side here, then you see this is nothing else but the result of the product rule, right? So you could write this part also up as the derivative of capital GV times beta V. And this is a simple ordinary differential equation. So I can take the integral on both sides and then just rearrange terms, move GV on the other side. And then this is what I would get. So I have now a closed form solution for the base Nash equilibrium strategy for a first price sealed bid auction with continuous action and type spaces. And note, it's agnostic towards the type of utility function of prior that I'm using here. So I only have mild assumptions here. So you could use here now a uniform distribution, a normal distribution. So this would give you a pure base Nash equilibrium. It would tell you exactly for each value that you might have for the good that is being auctioned off, what bid you should submit. All right. So for a standard first price sealed bid auction, you can actually say for a standard first price sealed bid auction with a uniform prior and just two bidders, it actually turns down that you have a linear bid function, which says essentially bid 1/2 of your value. All right. And this term is nothing else but the expected value of Y, given that Y1, so the highest, the random variable that describes the highest bid of the others, is less than my value. Right? So this is another way of understanding this bid function. This is not yet a proof that this is an equilibrium, I have to say. So for this to show, you might want to have a more extensive proof that essentially looks at alternative bids, right, and sees if and show that whatever other bid you use, it would always decrease your expected utility. Right? So I'm not going through that. It's just what I think is important, maybe for the remainder, is to understand how would you essentially get to a base Nash equilibrium, and why is this so different than maybe some of the other types of game theory that you've looked at. So important part is we are looking at continuous type and action spaces here. Right? And the bidders, the opponents are drawn from some distribution. That's their type. Any questions here? So this was beautiful in a sense. So when this paper came out 60 years ago, this was really a landmark paper in a way, right? So how would you actually, what is the right mathematical language to think about strategizing, right? So often, if you look at this supply and demand curves, this is looking at markets from a bird's eye view, right? So, but now we have a method and a model that would take the incentives of bidders and their strategic behavior into account and predict the outcome, right? For rational bidders, so to say, right? But the choice of utility functions is actually fairly flexible. Right? And we have a fairly complete theory for single object auctions. Turns out if you look at multi-object auctions, things are getting a bit trickier. Right? So one example would be the extension of the single object first price seal bid auction to an auction where we have, say, two objects, and say we have a combinatorial auction, very much like what we've been discussing all along now, right? So bidders are now able to bid on the individual items and on the package, right? So much of this literature on combinatorial auctions is really looking at the winner determination problem and or what we did before the break, how we can compute competitive equilibrium prices. This type of strategic behavior that is modeled as a Bayesian game, there is not a lot of literature out there, right? For these combinatorial auctions, which is an interesting observation. So why is that? So if you really take this simple extension, so this single object auction, and you extend it towards an auction with two objects only, where bidders may submit these bids on a single object or in the package, well, then actually we don't know an analytical closed form solution for the Bayes-Nash equilibrium strategy after 60 years. Right? So actually we bumped into this problem a while ago, and this is now 2 slides that should illustrate you what type of assumptions you have to make in order to get to such an equilibrium. Essentially, we ended up giving the problem a bit more structure. So we modeled now a reverse auction with actually 2 lots. So this is actually frequently used in procurement. So you have a particular contract, you buy, say, copper or wires or whatnot. And in order to secure supply in the long run, you split this contract into 2 parts. So you have 50% shares, and you allow the bidders to submit a bid on either a 50% share or on the entire contract. So this is nothing else but a form of a very simple combinatorial auction. In the language of procurement, this is often referred to as a split award auction. So we take the usual assumptions. So the valuations here, this is the costs essentially of the suppliers, are drawn from some prior distribution, again, F. And we made an additional assumption, namely that we know the upper and lower bounds of this distribution exactly, right? And again, the prior distribution in these Bayesian games is common knowledge. Bear that in mind. So everybody shares the same understanding of this common prior distribution. That is important. It's a strong assumption, by the way. It has been challenged, but it's a usual assumption that we're also going to make here. So then we made an additional assumption, namely that the efficiency in this market is known. So what do I mean by efficiency? We mean production efficiency. So this could be a market with either economies of scale or diseconomies of scale. Right? So to show you how this would play out, say we had BI times C would model the cost for producing the 50% share. If, say, your price for producing 100% of the contract, so both shares, is 100, then with C is 0.3, the cost for producing 50% only would be 30. So this means I have diseconomies of scale. So if I have to produce more, it's actually getting more expensive for me. In many markets, you have economies of scale. Then actually the game theory gets a little easier. With diseconomies of scale, it's a bit tricky, as I will show you in a minute. And I'm spending some time on this now because this is an example that we're going to revisit later on. So I hope the basic setup of this market is clear. So the important part now is that this is a market that has multiple Bayes-Nash equilibria, pure Bayes-Nash equilibria. So one is the winner takes all equilibrium. So in this market with diseconomies of scale. So this means both suppliers, or it might be multiple suppliers, they all compete for the grand package, for the 100% share, right? This is not efficient if you have diseconomies of scale. If you have diseconomies of scale, it would be much cheaper for the buyer if he would award 50%, because of course bidders have diseconomies of scale, right? So it would be the efficient trade to play the sigma equilibrium. Sigma equilibrium would mean the bidders both aim to win 50% share. It took us quite some time to derive the Bayes-Nash equilibrium strategies. You have to submit a bid on S, so this is the 100% share. In sigma, this is the 50% share. So what is very illustrative is the case where you have two objects and two bidders. Right? Why is that? We have an interesting pooling equilibrium that I will get at a little later. This means if both bidders want to find this sigma equilibrium, so then how would this look like? So this is an equilibrium where, independent of the cost draw, they would both submit the same bid, namely the highest, the upper bound of the cost distribution for the 50% share. Right? So independent on how expensive it is for them to produce. Why is that? Well, they can essentially collude, right? So, and then it's not that they just bid infinity on the 100% share. What they would need to do is they need to bid just competitive enough, just low enough on the 100% share, such that deviating to a strategy where you want to win the 100% share is not profitable for you in this first price auction. So this is a bit involved, I know, but it's a very common setup that you often find in procurement settings, right? So this is this second equilibrium, the sigma equilibrium. This is an equilibrium where the bidders have to coordinate, and that's not an easy equilibrium, right? However, for the bidders, it's the payoff maximizing equilibrium. So it's the one that the bidders would like to have, and it's also the efficient outcome, right? So as always with Nash equilibria, you have equilibrium selection problems. So picking one among these equilibria is tricky. Payoff dominance. So this one would be payoff dominant, but you don't know which one is being played at the end, right? Anyway, so why am I telling you this? I wanted to showcase to some extent that moving away from this single object environment to a multi-object environment, potentially a combinatorial environment, one where Sven has done so much work, is way harder, right? And you have to make very strong assumptions. What assumptions did we make? Well, our model was restricted to 2 units. We assumed risk neutrality, no idea what happens with risk aversion. We assumed publicly known parameters C, the upper bar and the lower bar. And it was still a multi-page proof and, very, very tricky. Right? So this should give you a bit of an idea how far we got with respect to Bayes-Nash equilibrium analysis. It's a bit frustrating, you could say. So it's, if you come up with slightly different environments, if you do comparative statics, as an economist would call this, so you do sensitivity analysis on different parameters, things can get very, very tricky. So this is by and large where we are today. So we have a very complete theory for single object independent private values models. We also understand value interdependencies. So if I give up the independence assumption, with multi-object auctions, we have Bayes-Nash equilibria for very specific settings, but a few only, interestingly. If you add interdependencies among the types or asymmetries or multiple objects, you typically end up at an intractable system of partial differential equations. Right? So this is not easy. There is some work on existence. So when would these Bayes-Nash equilibria exist? The first one was by Milgram and Weber in '85, and it's a paper that is worthwhile reading because it introduces distributional strategy. So this is the mixed extension of pure Bayes-Nash equilibria. So think of mixed Bayes-Nash equilibria. So you're mixing among different pure Bayes-Nash equilibria. Right? And that's something we are going to leverage a little later in this talk. Then there was work by Susan Athey, Jackson and Swinkles, and so on and so forth. I'm not going to go into much detail here, but if you compare that, so Nash equilibria, we have an existence proof. So we know that these mixed Nash equilibria always exist for normal form games. For the type of games that we are considering here, our knowledge is way more restricted. So this is one takeaway here. And even less is known about computation. So if you consider the normal form games that you're probably all well aware of, so you have a finite number of players, a finite number of actions for each of the players, then it took until 2006, 2009 until we understood how hard it is to compute Nash equilibria, mixed Nash equilibria in general. And it was shown by Skalakis, Goldberg, and Papadimitriou that it is PPAD complete, right, as a problem. This only holds for these types of finite games, right? For these Bayesian games that I'm discussing here, we know way, way less. So there is one paper by Kai and Papadimitriou, and they show that for a very specific setting, it's a set of parallel victory auctions where bidders have additive valuations except one with unit demand. Already there, if you want to compute the Bayes Nash equilibrium exactly, it's PP hard. So this is beyond the polynomial hierarchy. I was earlier telling you about the sigma to p complete problem. So this is beyond the polynomial hierarchy even, and can be considered completely intractable. Even approximating these Bayes Nash equilibria in this very setting was shown to be NP hard, right? So it might not come as a surprise now that there is fairly little work on computing Bayes Nash equilibria in these environments. So there is some restricted work by economists. Bardari, Athey, Bossert, and Seuken gave a very nice algorithm recently for specific setups, combinatorial auctions actually, and they're able with a certain type of best response dynamics to compute approximate Bayes Nash equilibria. It's computationally also expensive, but a very interesting approach. So the question that you could ask yourself now is, what is the value of an equilibrium solution concept that is in general intractable, right? So how can it be predictive if it is so hard to compute? Right? The second question that you could ask yourself, and that's the guiding question for this part of the talk, which is more of an outlook, is, well, maybe we can develop computational techniques that at least for subsets of games give you an approximation of the Bayes Nash equilibrium, right? One that does not require years of theory work to come up with a new equilibrium prediction, but that can be run maybe in minutes, right? So that's essentially what we're after, and that's the type of equilibrium computation that we're going to talk about next. Any questions up until now? Pause for a minute. Nope. All right. So what do we know about equilibrium computation? Equilibrium computation in general in games has a long history. So it goes back to 51. Remember, Nash's original paper was published in 51 as well. So, and in the same year, Brown came up with a method that was referred to later on as fictitious play. So we're, people have looked at best response dynamics, and you play in fictitious play, you play the best response to the historical play of or distribution of the play of your opponents. Right? Much later, in the early 2000s, in computer science, people came up with gradient dynamics. So rather than chasing pure equilibrium in these games, you're essentially aiming for the mixed extension of the game, and you're following the gradient of your utility. And we are essentially doing something similar in the next couple of slides. Unfortunately, it's also known that these types of best response dynamics or gradient dynamics do not converge to Nash equilibrium in general. So it's a very restricted set of games, such as potential games or certain types of zero-sum games, where you can expect these dynamics to converge. And I'm only talking here about finite games, right? Not about the auction games that I was telling you before. And what is known is that if you follow these dynamics, and this is covered under a larger umbrella of no regret algorithms, then you end up in a coarse correlated equilibrium, which is really a large superset of the Nash equilibrium, right? And it might even contain equilibria that are dominated, that have dominated strategies, right? So it's what you ideally would want to find is really the Nash equilibrium, right? An exact computation of these Bayesian Nash equilibria would be, it could be formulated as an infinite dimensional variational inequality. And even there, we are kind of scratching the surface, right? So these are notoriously hard to solve. So the questions that follow from this is how, suppose we want to implement something like best response dynamics or gradient dynamics, how would we even do that in this infinite dimensional space? Right? So we have an infinite type and action space, right? Or continuous type and action space. So how would you implement these algorithms that were designed for finite games? And even if you could do that, when can we expect these dynamics to actually converge to the Bayes Nash equilibrium or to an approximation of this Bayes Nash equilibrium? All right. So this is these are our next set of questions. So let's step back for a minute. We will draw a lot on gradients or gradient ascent, essentially. So before we get there, a brief recap of gradient descent, even though I understand that in this round, this is bears no surprises to anyone. So we have, say, some convex optimization problem, as up here. And then how would we find like a minimum here? We could do gradient descent. Where does gradient descent come from? Well, I think the basic idea goes back to, well, say you do a Taylor approximation of the first order on this red function here. And then you could go along the this tangent line, right? But you don't want to go too far, right? Because if you go too far, you know your estimate of the next point is maybe far off. So what you do is you add a penalty term here, right? This is kind of the Euclidean norm squared here. And if you take the first order condition of this term, well, what you get is this kind of very well-known recursive formula that essentially determines the steps in gradient descent, right? So you take a point, say in here, and then you go a step in the direction of the gradient, and the step size is eta, and that determines then your next point that you're looking at, right? And you do this until essentially you converge to the minimum. And I don't have to tell you, there are also for discrete functions you have subgradient descent, and then there's projected subgradient descent, and so on and so forth. Right? So this is, I mean, we are living in an age of neural networks. Gradient descent has become super popular, as you all know, right? So it's the workhorse in machine learning and neural networks, and this is just one of the things that I sometimes show my students, where we have different parameters like different step sizes, and momentum is often pure gradient descent is zigzagging in some curves. So you want to keep the direction. So you add another term, which is called momentum. And these are hyperparameters that you can tune. And this is just different versions of learning rates and momentum and how they play out and how fast they find the minimum of some convex function. Right? So what I want to tell you is there is a whole slew of convex optimization functions. Many of them you're certainly aware of. And there's a lot of hyperparameter tuning, but ultimately they've been super successful in machine learning and data analysis, right? So essentially what we want to do is simultaneous gradient descent. So this is how you can understand these gradient dynamics. So essentially each agent follows a step along this gradient, right, in each step. So suppose you're given some normal form game here with bidders I, actions A. This could be a discrete set of bits, say, and utility functions again. Then each bidder in each round, T, would submit a BIT, so the bit of bidder I in round P, then you observe the gradient of the utility. How we're going to do that, I'll show you in a minute. Right? Suppose you have this gradient of the utility, well, then the rest is fairly simple. You add that utility gradient, multiply it by eta. This is again your step size. Go a step in that direction. If this leads you out of the feasible region, say you all of a sudden have a negative bit, you project back, and that is your next bit. All right, and you do that over and over again. In each round, every bidder does this. Right? And the conversion of gradient dynamics is, well, when can we expect these gradient dynamics, where every bidder is doing that in every round, to converge to something like a Nash equilibrium? Any questions here? So remember at the beginning, I was telling you about these Bayesian games. So this algorithm that I'm showing you here is really about finite games. But what you can do is you can imagine that the ex-ante state of the Bayesian game is a complete information game, just one where you bid a bid function rather than a simple bid. Right? So this is the first insight. And second, ex-ante, the type and action space is infinite dimensional. So we need to bid this bid function. And we can approximate this bid function, right? That's essentially what neural networks, or any other type of learning technique is made for. So rather than finding B directly, what we do in equilibrium learning is we could mimic the bid by a neural network. And this neural network is pi I, and it has two types of parameters, Vi and theta I. Right? So Vi are again the types, right? So the value that you draw. Theta I are the parameters of the neural network. See, there is a question.
Yes, can you hear me, please?
Yes, I can hear you.
Yeah, thank you so much. Did you try other algorithms in mathematics, like Taylor algorithm or maybe bisection instead gradient ascent? Because always people use this method in machine learning processes.
Yeah. Short answer is no. There is plenty of room to do things differently. You could use second order methods. You could use Newton methods if you have a second derivative, and so on and so forth. I think the beauty, and that is probably why many people use gradient descent or gradient descent, depending on what your loss function looks like, is it's super fast and simple, right? But there are alternatives. So, but let me not get there. Maybe. And you can replace this. What I'm going to do now is I'm going to show you two methods, and there is plenty of wiggle room to use different methods and maybe make things more effective, right? So, and that's why I'm giving this talk here, because you're all working on your PhD thesis. Maybe there is some food for thought and some different ideas, right? So I'm not saying that what I'm presenting to you is the only way on how to do this. I'm telling you this is one way to do this, and actually, we get nice results, as you will see a bit later, right? And it's ultimately a topic that is heavily ingrained in optimization, as you've seen already.
Sure, thank you. Yeah, got it.
Okay, good. So please jump in if you have any other questions. So now, and by using these neural networks, one of the nice things is that we are now playing the game in the finite dimensional space again, not in an infinite dimensional space, because we have a finite set of parameters for these neural networks. So essentially, rather than finding these Bayes-Nash equilibria in this infinite dimensional type space and action space, we now have these neural networks, and the number of parameters for these neural networks is finite, right? It's the weights and biases of these neural networks only, right? And that's something where we can actually use and employ gradient descent. Right, this is what I just told you. So, probably everybody has looked into neural networks recently because it has become so popular. At least in a computer science department, you can hardly hide from neural networks. So, but let me discuss a few of the fundamentals here. So, and these are the types of simple feed-forward networks that we're going to use. So we have these, inputs, xi here. Then we have the weights and biases. This is the weights and the bias for a particular node, and an activation function. And this could be a sigmoid function, very much like in a logistic regression, or it could be a reload function like the one depicted on the right-hand side. And then in a forward pass, you feed in the new inputs and it fires a particular output, right? Then typically you have a loss function, right? And this loss function is then used to evaluate the output, right? So if you want to classify whether something is a cat on an image or not, well, it would be some binary loss function, right? And you feed it with a lot of training data, and you want to understand how well your weights and biases are suited to produce the right outcome. So this is typically what is being done. So it might be a quadratic loss, say. We replace the loss function by the utility function, right? Because we don't want to minimize a loss. We want to maximize the utility of the players, right? So just flip signs. And this is the type of utility function that you've seen before. And you might now ask, okay, where does the training data come from? Well, just let these neural networks play against each other, right? And they would generate new instances of data. It's not, it's not a steady distribution. So because the bits change over time, obviously, right? And that's what makes these types of learning tasks in a game theoretic environment so much more challenging than your standard, image recognition in a way, where you largely draw on the same distribution, right? Cats look the way how cats look, and they don't change. You might have different pictures, but the underlying distribution you can assume to be the same. Well, that's not true in a game theoretic setting, because players adapt. So this was the forward pass, and now the question is, how do we learn in these neural networks? And this is referred to as backpropagation, where people use gradient ascent now to adapt the weights and biases, right? You feed in some input, you understand whether your output was correct or not, or in our case, whether our bit was winning or losing. And then if it's losing, you adapt your weights and biases to become better. And an epoch is defined as one pass through the training data set. This is not something we have. This is kind of standard neural network terminology just. And then you have various types of optimizers. I mean, you've been asking about alternatives. So in neural networks, there's plenty of optimizers, stochastic gradient descent, ADAM, and so on and so forth. You pick whatever is your favorite. And what is important now about these neural networks, what is very useful for our purposes, is the universal approximation theorem, right? That goes back to Kurt Honig in Vienna in the early 90s. And there are various versions of this universal approximation theorem, but essentially it says that these multi-layered neural networks can represent arbitrarily nonlinear functions. And since we don't know how a bit function looks like, that is a very useful property. So essentially you could think, well, so it's fairly straightforward to essentially just have neural networks play against each other. And then you do your usual learning step. You just use standards, feed-forward networks, things is done, right? So the difficulty if you do equilibrium learning in auctions is that the ex-post utility function is actually discontinuous. So, gradient-based methods on discontinuous functions, that's a bit tricky, obviously, right? So, because it's probably best illustrated by this picture. So you have, this is the view of one particular bidder, I, and B minus I super 1, so this here, is the highest bid of an opponent in a particular auction. Well, then every bid that you submit below your highest opponent's bid is obviously has a gradient of null, right? Every bid higher than the highest opponent's bid has a negative gradient. So guess what happens? Well, if you train your networks, ultimately all the bidders will bid 0, right? So either the gradient is 0 or it points downwards, right? So one of the things, if you want to employ neural networks in this environment, is you might think of some smoothing technique, right? And the smoothing technique that we used here is evolutionary strategies. So rather than evolutionary strategies is one way to compute a pseudogradient. So essentially, you're really smoothing this curve, right? So you get a signal in and around this discontinuity. Okay? Right, and with that background, I can now guide you through a pseudocode that gives you an idea of how such gradient ascent, simultaneous gradient ascent, might actually look like if we employ these neural networks. So we have as an input agent, we have an initial policy. So this is our initial set of parameters. We pre-train them, but let's not get into that. Then these are these initial parameters. Then we need some parameters for the evolutionary strategies and some noise parameter and a step size eta and a batch size, right? So what we do in each round of this auction is, and I know this looks a bit convoluted here, but it's not that difficult, you will see. We first draw a batch of valuation profiles. Say you're in an auction, what would that mean? One instance in this batch would be one auction where, say, Sven and I, it's a 2-bidder first price bid auction. We make one draw from our valuation distribution, right? This is, and we draw many, say to the power of 18. That would be around 260,000. All right, and then we compute for the current strategy. Remember, current strategy means the current set of weights and biases of our neural networks. So Sven has a neural network, I have a neural network. We compute an average utility that we achieve with our current strategy. And then we sample perturbations. So essentially what we do is we add Gaussian noise on our weights and biases, right? So rather than playing the original strategy, we do some permutation of these strategies. And we evaluate each of these strategies and try to find out, given the current opponent strategy, how much better or worse would I be with this new strategy? And that is phi here. Well, and now we can compute the fitness weighted perturbation noise. And it has been shown in other work that this is something like a pseudogradient. So essentially, we just multiply this fitness of this particular perturbation of weights and biases times the perturbation noise that I was adding. And we take the weighted average of this. So this is now our pseudogradient. So you will see this is obviously a bit more computationally expensive than our standard gradient ascent, but it does the trick. So we get a gradient here, or an estimate of the gradient. And now we do the usual. So this means in here, to the current set of weights and biases, we add this term here, delta phi. What is delta phi? So this is our usual eta, the step size, plus the evolutionary strategy pseudogradient. Right? So this is our delta phi. And this is then the next incarnation of our bidding strategy. All right. So this is one way on how you can implement gradient dynamics in a game that has infinite or continuous type in action space. So can we say anything about convergence? So in general, it is known that these types of gradient dynamics, independent of the implementation, also converge to coarse correlated equilibria. So this is this large superclass that I was telling you about of the Nash equilibria in finite type but continuous state in action. So this is not yet where we want to be. Then we've discussed a bit earlier, so these types of Nash equilibria can also be modeled as variation in inequalities. So here, this X is the feasible set, and the gradient of F would be the gradient of our utility function, right? So what we know is that if the gradients of our utility function are monotone, then gradient dynamics converge, right? So this is very much like what is known about variational inequalities in general, right? So if you have monotonicity, then this would actually mean, if you have strict monotonicity, that we have a concave utility function, or only concave utility functions, then this is known to converge. Unfortunately, this is not that easy to check. So remember, we have this, somewhat more elaborate ex ante utility function with some prior distribution, just to check whether this expected utility or the gradient thereof would be monotone, does not turn out to be easy, right? To characterize. So we don't know a priori, actually. So is there anything else we can draw on? Well, we could make some bit more strong assumptions. And one of the assumptions is, well, let's restrict our attention to games or to a strategy space where the strategy is symmetric. So this is not an unusual assumption. So remember the very first example that I was showing you about the first price seal bid auction. So we made this symmetry assumption. This is very common in auction theory, that you assume that all the players are totally symmetric. Right? And if you only allow for these symmetric strategies, then it is essentially, you can understand this as a potential game. For potential games, we also know that gradient dynamics converge. Right? So this is a bit beyond this class, but by and large, that allows us to say, at least for this restricted game, that in any smooth auction game with this symmetric price and symmetric strategies, this symmetric version of NPGA with appropriate graded upstate sizes converges to local ex-ante kappa as an approximate Bayes-Nash equilibrium. So we need to make this restriction to symmetry in symmetric strategies, really. But if we don't trust this, there might be some asymmetric, some deviations. We can always empirically check, right? And this is also what we do in our empirical work that I'm going to show you. So you can always say, well, stick to this first price seal bid auction where Sven and I are playing against each other. Then if you found your Bayes-Nash equilibrium strategy, you can define a grid of fine-grained deviations from our bid function and check whether any of those would give you a higher expected utility. Right? And then if this is not the case, you can maybe certify that this is a Bayes-Nash equilibrium. Right? This is computationally more expensive, obviously, but it gives you at least an empirical proof. Right? So does this at all work? So we essentially went through a large number of different environments, different types of auctions, so single item auctions, very much like the one that I was showing you earlier. Then we looked at multi-unit auctions, and we looked at combinatorial auctions. Here we analyzed a very famous setting, the local global setting, which is very simply, you have again two items. You have two local players. They only want one of these items, and a global player who wants the package, right? And there are various types of payment functions that have been analyzed in the literature that are very relevant to spectrum auctions. So I'm not going to go too much into the details here, but you can understand these course selecting auctions as competitive equilibria. So at those prices, if bidders are truthful, nobody would want to deviate. And the Bichler-Clark-Groves auction is one that is strategy proof, but not always course stable, right? The outcome. Anyway, you don't need to understand the very details of these payment functions. They turn into different types of auctions. And this is, we looked at this for independent private values, for correlated values, and for very large auctions as well, with 8 items and 6 bidders, right? And for auctions of this size, just let me remind you, we have no idea what the Bayes-Nash equilibrium strategy is. So for the small environments, and that's why we picked them, we actually do have an analytical solution, right? So A colleague of ours actually went through the job to really derive these Bayes-Nash equilibria for these very restricted settings. And the reason why we focus on this is it provides an unambiguous baseline to compare against. So if we find this equilibrium function, we know it has to be the Bayes-Nash equilibrium strategy. But obviously, the way more interesting environments are those where we don't know the Bayes-Nash equilibrium strategy. Right. And the last environment here really is the one that I was telling you about at the very beginning. So the one with the split award auction, where we have again 2 lots, and here the bidders are also multi-minded, so they are interested in both the small lots, the 50% share and the 100% share, but different equilibria might emerge. So this environment is super interesting because we know that there is more than one Bayes-Nash equilibrium, and it would be interesting to see whether these types of gradient dynamics would actually find at least one of those equilibria, or they will not. So a few empirical results to hopefully convince you that this is an interesting area to explore. Right? So we have we defined a utility loss. So this means in those environments where we know the analytically Bayes-Nash equilibrium strategy. So I was telling you for the first price sealed bid auction, the simple one with a uniform distribution and just Sven and me playing, then this equilibrium strategy would actually be linear and be V half, right? I would just bid half of my value if I'm a risk neutral. But these equilibrium strategies, depending on the prior and depending on the number of bidders, can be very, very different, right? So they might have all types of shapes. And so what we are looking at here is the first price sealed bid auction single object with uniform risk neutral bidders, with risk averse bidders, or with Gaussian priors, and with different number of bidders. And the column to look at is this one, which shows you what the efficiency loss is. And you see that the efficiency loss, and this compares the strategy as an outcome of this learning exercise to the analytical Bayes-Nash equilibrium strategy. How much worse would the learned strategy be compared to the analytical strategy? And it turns out that we are very, very close in terms of utility. So how long does it take to learn? Well, depends very much on the prior. So with the uniform prior, we are sometimes very fast. With the Gaussian prior, it needs some time until you're precise at the tails of the distribution, and it can take, say, 1.5 hours to converge. This is now an environment that is asymmetric. So I was telling you, we have some evidence that with symmetric auctions, so this means symmetric priors, they all draw from their values from the very same distribution function. Then we have some evidence that this method converges. But this is different for asymmetric first price sealed bid auctions. And yet, so this is the solid lines are the analytical solutions, the dotted lines are describe the outcome of NPGA. So that's how we call this technique. And you see this is very close, even for asymmetric environments. Then, this is these combinatorial auctions that I've been talking about with different payment rules and independent private values. Also here, the utility loss is very small. You see sometimes it's even negative. This means this is just, you can't be better than the analytically Bayes-Nash equilibrium strategy here with unilateral deviation. So this is really numerical instabilities. So this is very, very tiny differences in the expected utility. And what we also show here is the root mean squared error to the analytical Bayes-Nash equilibrium strategy. So this means the strategy that we learn is indeed very, very close to the analytical one, very much like what you've seen in the last slide. So here is one graphical description. So I was telling you in this local global model that Sven is very much aware of. There's the global bidder. He has a very simple dominant strategy, which is the red line, and the local bidders they have a somewhat more involved strategy, and NPGA is spot on, I would say. Right? Same thing if we add correlation. So also for this environment, we actually have an analytical solution if the valuations or types are correlated. And again, the root mean squared error and the loss is super small. And here we come to an environment that is now very large. So this is an environment where we don't know the Bayes-Nash equilibrium strategy. And this is one of the interesting ones. So many of these LLG models, as I was telling you, were really inspired by certain types of spectrum auctions, where you have, for example, local providers in Canada competing against the large telecoms, right? And you want to understand, well, how in such a combinatorial auction, actually in Canada and in many other countries, they are using combinatorial auctions to award spectrum to telecoms. So in a stylized model, at least, where we have, say, 4 local and 2 global bidders, how would the equilibrium bid strategy look like in this model, at least, right? And so far, this was elusive to compute. And here you see not the equilibrium strategy, but the utility and the utility loss. So the utility loss goes down, as you see, quite quickly. And the utility for the global and the local bidder actually converges also after, say, 250 to 300 rounds. So think about this. In general, the recipe is fairly simple. Just have all the bidders do gradient descent on their utility function. The implementation is a bit more involved, and it still gives us apparently a fairly good prediction, and we can compute the utility loss. Now we don't have, this is an estimated utility loss, because obviously we don't have the analytical solution, but we can compare against many, many other strategies and see if any of the other strategies is better. Well, last but not least, this is the split award auction, the procurement auction that I was telling you about. So this is a bit convoluted, this picture, but let me explain. So this is the 50% share here towards the left, and here is the 100% share. And now you see that we have a gray range here, and this is the allowed range of split equilibria. So this sigma equilibria, if you remember. So the payoff maximizing equilibrium is the highest. So essentially, I was telling you that these 2 suppliers, so this is the environment where we have 2 suppliers and 2 objects. So these 2 suppliers, if they would go for the 50% share, they would just both bid the upper bound of their cost distribution, the upper bar. They would tacitly collude. And that's an equilibrium. And at the same time, they can't bid infinity on the 100% share. They need to bid just in this range here, just competitive enough such that it doesn't make sense for the other one to deviate. Right? And interestingly, in PGA, this is the blue dotted line, finds equilibrium strategies that implement just that. And it always finds the payoff maximal strategy. So the solid line marks here the winner takes all equilibrium, the second pure equilibrium that we could identify. And that's an equilibrium that we never find. We always go for the payoff maximal one from the point of view of the bidders. All right, let me maybe pause here. I hope I could convey the basic idea, right? So in general, finding, quick summary, in general, finding Bayes-Nash equilibria in this continuous type in action auction games is super hard. So at least for restricted environments, we already know even the computational complexity. And this is way beyond the type of optimization problems that we typically work on. So what I'm telling you now is, well, pick a very simple optimization algorithm, namely one that was designed for convex functions, and have these bidders play gradient descent simultaneously in each round. And yet, even though the general problem is super hard, there might be environments where we actually always find the Nash equilibrium, right? So the difficulty is maybe not so much how we implement the method, but the challenge, and there's a whole group of people working on this questions now, is how can we certify? When do we know a priori that an algorithm like this would converge? Right? So that's the hard part. Are there any questions at this point? No? Then let me show you a second variant. And really, the reason why I'm telling you all of this is I think this is a fruitful area, in particular for fresh PhD students to work on, because I think there are so many open questions, which is always nice, right? So another technique that we developed with Max Fichtel and Matthias Oberlechner was a technique that does not use these neural networks, right? And it works on the discretized version of the game, right? So I was telling you, we have, the challenge is these infinite dimensions. So we have continuous type and action space. So why not just discretize it? This is what you do in numerical math all the time, right? So that comes with a few challenges, but let's do that. This is a technique that I will refer to as SODA, simultaneous online dual averaging. And the key difference, though, is not the discretization. It is that here we search for distributional strategies. We search for mixed Bayes-Nash strategies and not for pure strategies. All right. And why is that important? Well, it is important because now our expected utility is linear in the distributional strategies. This was not the case before. And by being linear, we can actually draw on a theorem that was, published only a few years ago, 3 years ago, by Metikopoulos and Su. And they show that if a complete information game with finite dimensional continuous action space, and this is what we have in the discretized version, is pseudo-concave, ours is even linear, and the sequence of pure strategy profiles, so the sequence of play of the gradient dynamics converges to an A star, then A star is a Nash equilibrium. So this means even if you don't know a priori, if you have it run and the thing converges, well, then it has to be a Nash equilibrium. Right? And that is super helpful because I will show you, at least for the type of games that we look at with, moderate amount of bidders or even symmetry, we can run this super fast, right? Really, sometimes in a matter of seconds. So one step back, so far with MPGA, we were talking about these types of strategy, pure Bayes-Nash equilibrium. Important for you to understand. So we have a particular cost draw V or type or your evaluation, and the bid function beta gives you a specific bid that you should submit. All right. So a distributional strategy gives you a distribution. It tells you, well, with a particular probability, you should pick this bid, or this bid. So AI here is essentially the bids you can submit. So we don't play this in the continuous type and action space. We play this game in the discretized version. So this is what you see here. So we look at discretized distributional strategies. And the dots here, the S here, tell us essentially with which probability should I submit which bid. All right. So then this is essentially how I can describe our joint probability. So it's really the sum of all nu is the types of a particular bidder I, and mu I is the possible bids that a particular bidder can submit. And SI is the probability with which I play this particular type mu I plays bid mu I. All right. And with that, I can just now write up my expected utility. So this is what you see here. And I have to sum over, and this is now written up for only 2 bidders to make this a bit more tangible. So I have a bidder I and a bidder J, and I have all their types and their actions for bidder I and for bidder J. And I sum over all of those and multiply the utility that I can compute a priori. If I know if Sven submits 10 and I submit 5, and my type is 7, say, I'm losing, so my utility is null, right? So I know what these utilities are. These are parameters. And these are the probabilities with which I play these various types and combinations of types and actions, right? I can rearrange these terms and then I get this one here, right? So this is now the type of probability that I'm interested in, my probability in playing any of these type and action combinations times this part, which is now turns into a parameter as long as the probabilities of the opponents are given. And this, I can have a shorthand for this SI times CI. CI is this here. And with this, I can compute really a best response, right? So at each state of the game, I look at what is the probability of Sven playing particular types and actions. So this would be his, this is all ingrained in C here. And then I'm trying to maximize my utility by multiplying S times C. And I'm trying to, the variables here are SI. So this is a simple linear program where I maximize my expected utility. This is what I've shown you here. This is my expected utility. And subject to that the sum of all the probabilities that a particular type of myself bits, so that of all the probabilities S needs to be needs to equal the marginal distribution, right? So the prior distribution that I'm having. So remember, these Bayesian games have a prior distribution. I know with which probability Sven has a value of 1, 2, 3, or 4. Right? So this is given, and this is what this term is all about. And the rest is, I don't actually have to even just spend a lot of time on it. Think of it as gradient descent again. Now in this discretized game, right? Rather than gradient descent, we use aversion. And I was telling you there are zillions of different versions of gradient descent that all have different convergence properties, right? Some of them are nicer. Dual averaging is a version of mirror descent, mirror ascent in our case, which rather than this Euclidean regularizer that I was telling you earlier, it uses an entropic regularizer. So its details I'm not going to go into. Think of it really as a gradient descent technique, right? And also in here, you essentially update in your dual space, in this case, the a score function. That's what you enter into a link function G. And this link function has this entropic regularizer. So even if you're not into convex optimization, these are somewhat more advanced methods that have slightly better convergence properties, and they don't need any optimization here. So you have, essentially you can turn this into a simple formula that you can compute readily. So again, does this work at all? So this is now working on this discretized space. So how would you have to think about this? These observations are again our types, right? So this is the iterations. So originally, when you start the game, you randomly initialize this grid. So again, this is action. So types and actions. If this is Sven, he might have a very low type, so a very low valuation, and these are different. The different gray shades are just different bits and how likely he is to submit one of these bits. And then we have this simultaneous gradient descent type of technique, and we play this for say 300 rounds. And what we get, so and this is actually what we play here is the notorious example that I'm always using: 2 players, Sven and myself, in a first prize seabed auction with a uniform distribution. So indeed, what you see, the red line is playing 1/2 of your valuation. And that's actually also what the black shaded cells tell you when you bid 1/2 of your value. So a question that you might ask now is, does this epsilon-based Nash equilibrium in this discretized version of the game actually approximate the continuous game. Right? So that's maybe not super clear. So maybe you find, if you discretize, you might find a very different type of equilibrium bit function. So we have some theorem here that shows you that if you find an epsilon-based Nash equilibrium in the discretized game, it's also going to be an approximate equilibrium in the continuous game. So we are not too far off, so to say. Right? So, but that's also a bit beyond this class. But by and large, this is a first example. And what is stronger now in this type of equilibrium computation is we know that if it converges to a pure strategy equilibrium, it has to be the Nash equilibrium. Right? We don't know a priori if it converges, but maybe it's not so bad because, and that's what you see here now, it is for the environments that we've seen so far, super fast. Right? So this is common in affiliated values model. This is a specific type of interdependent value model that is very common in the literature. And you see here the dashed line is the analytical solution, and the blue shaded line is what Soda really finds. And the main difference is here, so the utility loss is equally small, but we are way faster for these environments, right? So we can solve this in less than 2 minutes. All right. And that is also true for asymmetric environments. So I'm just dumping some pictures on you here just to provide some evidence. First of all, what you should take away, in a fairly large set of environments, we do converge, which is, a priori, there is not necessarily a reason to believe that we do, right? And we are pretty much spot on. And this is, again, the type of combinatorial auctions that we've been looking at. So with different types of payment rules, again, details, it doesn't matter what the exact mechanism is, but here again, we can compare against the analytically based Nash equilibrium. Again, the utility loss is super small, but we can compute this super fast, so in less than 3 minutes. So again, not so bad that we don't know, maybe a priori, it would be nicer though, whether it converges, but if it converges, we can say something about this being a Nash equilibrium. Still, we are checking. Right? Well, and last but not least, this is now the split award auction that I was telling you about. Same picture, almost same picture that you've seen before. Again, this technique finds this weird pooling strategy. And it bids just high enough, or low enough, I should say, to avoid any deviations, right? So we're doing quite well. All right. So a few summarizing remarks here. The question now is, we have this super simple technique, if you think about it. Maybe not in implementation, but by and large, we are following the utility gradient, and each bidder does this, and we converge, even though the problem in general, we know also is super hard. So what are instances where this doesn't converge, right? So it obviously can't always work. So I'm having a super hard problem, and I'm solving this with gradient descent, so this would be too nice, right? So this cannot be. So here is an example of a bilinear game. So these agents here have opposing interests. We have the agents 1 and 2, and agent 1 has the action X, and 2 has the action Y. And now the utility of the first bidder is, well, let's bid X times Y, or let's evaluate X times Y, and this is my utility. And the utility of the second bidder is just opposed, so it's minus XY. So this is a game where the only Nash equilibrium is really in the interior. So if both bid null, then it would be an equilibrium. Any other point is not an equilibrium. And this is very much like the vector field that you will see now of matching pennies, right? So you have totally opposing interests here. And so this here would really be the Nash equilibrium. And if you look at the vector field, then it really orbits around the Nash equilibrium. So if you do a gradient descent, then you're either following the orbit or in the worst case, if you have large step sizes, you might even diverge. Right? So people have looked at setups like this because these types of non or zero-sum games are often used as a model for these generative adversarial networks. So this is why zero-sum games have gotten a lot of attention in the machine learning literature. And people have looked at different ways on how you get around this. But in general, these are games that serve as an example that gradient descent does not necessarily converge in any game, right? Which would have been too nice. Right? There is even a statement, it's a very, very tricky paper that largely draws on dynamical systems, that no possible game dynamics leads to Nash equilibrium in all games, right? So that's what we know. And we also know by now that if we have games that only have mixed equilibria, then these gradient dynamics are also not a good guideline. So what we don't know yet, maybe some of you can help us in the future with this, is can we correctly classify those types of games and those characteristics when we do converge? So we have a lot of empirical evidence, but a precise characterization, I think that is still to be done. All right. Maybe get to an end here. I was telling you about NPGA. This was this technique that learns pure epsilon-based Nash equilibria in games with neural networks and self-play. Right? And I was trying to convey to you, well, everything we do here is standard optimization, convex optimization. Right? We add lots of bells and whistles to make this work, which is more on the technical part, but it's simultaneous gradient descent. That's what you should take away. We can approximate pure Bayes Nash equilibria in auctions with interdependent values, different utilities, and so on and so forth. It works empirically quite well. We have some convergence guarantees for stricter assumptions, so symmetry even in the strategies is what we need to assume. And then I was telling you about the second technique, SODA, where we learn distributional strategies. And the nice thing is not only that in these small environments, not in large ones, but in the small environments that we were looking at, we know that if we converge, then it is also a Nash equilibrium, which is very powerful, essentially. Right, and I think the key takeaway from this should be numerical methods can help us push the boundaries of equilibrium analysis. I hope you understand what are the white spaces here, right? So this Bayes Nash equilibrium analysis has really been the standard approach to analyze small scale markets. We want to understand how strategic bidders would behave in these markets. And it turns out that while this works super nice in single item auctions, if you go to larger markets, and much of what Rakesh has been talking about, or Moshe or myself, are larger multi-item markets, right? There, we typically don't know the Bayes Nash equilibrium strategy, right? So, and what I'm arguing for is, I think there is a lot of room to explore and a lot of room to develop numerical techniques, very much like what people have done in engineering to come up with equilibrium solvers. And maybe some more philosophical insight. The experimental result that I was showing you suggests that given that we can solve this with gradient techniques, even though the general problem of finding Bayes Nash equilibrium in these continuous type and action games might be super hard, there seems to be subclasses that are not so hard to solve, that can even be solved with simple gradient techniques. And that's, I think, an interesting and open question. So where are the boundaries of this technique? All right. So with this, I'm open for your questions. Shameless plug. So I've written a book on market design a while ago on the first that covers elements of the first part of this class. And the last bullet point here is a paper that discusses parts of this talk here on NPGA, essentially, if you're interested. Thank you for your attention, and I'm happy to get questions if there are any. Thank you.
No questions. Nothing. Okay. Martin, I have one for you. Can I get an autograph?
Sure.
Probably not today, but anyway. Too bad.
All right. So
Um,
maybe some of the things have to sink in. So thanks for listening in, and glad that you liked it. So if I'd be happy to respond to comments even later. So I might depends. So this has been the very last class, right? And you had a really tough week. I know that. So I'll be happy to be around for the exercise session. I have some easier and some tougher ones. Maybe we can look at one or two of those. If not, that's fine as well. It has been a very long week with lots of exercises for you. But I'll be around. And other than that, I'll see you later, hopefully.